My name is Oren. This is Haidi, Shaelyn, and Kendall, and we are the Smart Pen and Smart Nebulizer for smarter asthma care. Asthma is a chronic respiratory disease that affects 262 million people and causes 455,000 deaths annually worldwide. Sudden asthma attacks irritate the airways and are caused by physical activity and environmental triggers. Patients take preventative medications and carry a rescue inhaler for when an asthma attack occurs, but by that time it's too late. Attacks are unpredictable, debilitating, and they cause inflammation that is uncomfortable and can cause permanent lung damage. Inhalers provide short-term relief, but the powdered medication inside can cause its own problems like dry mouth and coughing, which only serve to further irritate the airways. Inhalers also require coordinated inhalation with actuation, but this task is difficult for many patients. Finally, doctors need accurate data in order to build treatment plans and adjust prescriptions, but most patients misreport their inhaler use. Nebulizers are similar devices that atomize liquid medication into a fine mist. These devices are better because the vapor soothes irritation and delivers medication deeper into the lungs. However, they're quite large, they require an outlet, a long setup process, and 10 to 15 minutes of treatment.
So for our solution, we came up with a set of two devices, where the first one is a wearable smart pen, and this can record environmental data and upload it to our smartphone app, and this will help the user identify their asthma triggers in their local surroundings.
And for our second device, we have the Smart Rescue Nebulizer. This nebulizer is ready to dispense precisely metered doses at any time with intuitive one-step activation. It does not require breathing to be synchronized with a button press, and it reports nebulizer usage data to the app to be used by the healthcare providers to adjust the treatment plans.
This product is for asthma patients who regularly encounter unpredictable environments and allergens, but it'll be especially useful for children and patients with disabilities. This is the group that most underreports their inhaler usage, and they have the most difficulty coordinating their breathing when using their inhaler. This group is also unable to communicate when they need to use their medication, and so helping caretakers predict asthma attacks with the smart pen is crucial. Overall, the total addressable market for rescue inhalers is $5 billion. We calculated that we can target up to $230 million via our early adopters.
So here we have the Smart Nebulizer. For our project scope, we needed to design and build a working ultrasonic mesh nebulizer to eliminate the mold hovering cotton sponge used in the last year's design, as we can see here in this picture. This device also needs to be a pocketable, standalone, wirelessly rechargeable unit with all the electronics fit inside it. And it also needs to be easily deassembled for cleaning, and there's no leakage in there. Lastly, we needed to make sure it's comfortable and user-friendly.
Our design approach was to start by identifying problems and brainstorming possible solutions. We sketched the best concepts and used SolidWorks and rapid prototyping to validate and improve each iteration until we reached our final product. Throughout the design process, we followed 3 guiding principles. User-centered design, making our product safe, comfortable, and intuitive. Designing for manufacturability, avoiding thin features and weak print orientations to make our 3D print successful. And finally, always considering the integration of our mechanical and electrical subsystems at the end of the process.
And for our structure, our nebulizer is a slim vertical design inspired by the popular vape pens used in the market now. It has 5 main parts that could be separated easily for cleaning. The lower half is separated from the top half by a lipping groove to keep the electronics part dry. Here we have an exploded view of our design. The top half consists of the upper body. Here on the right we have the mouthpiece, and here we have the cap that covers everything. And then on the top we have the capsule, and the bottom part has the electronic housing along with the door, and we have the battery, the PC boards all sandwiched together, as well as the button board. So for the mouthpiece, we ensured that our design would be comfortable for the lips. We added a one-way valve to allow the user to inhale and exhale normally while using it, and to avoid any condensation or mold in the airway. And finally, to secure the mouthpiece to the upper body, both vertically and horizontally, we use a lip and groove and mounting and an L-shaped hook. So the goal for the cap design was to protect both the mouthpiece and the capsule from any damage, germ contamination while it's in a pocket or any of the user's purses. It also indicates the proper orientation of the device by designing the hinge to open away from the user, allowing the medication to go through the transducer and get dispensed properly.
We included an integrated multi-dose capsule that eliminates the need to fumble around with separate, single-dose ampules of medication. A spring-loaded rubber valve releases a single dose from the capsule when the device is activated. This quarter-turn snap lock provides tactile feedback when the capsule is secure, allowing for easy capsule replacements when it's empty or when the user wants to switch instantly between their preventative and rescue medications. When the medication is released from the capsule, it enters a metering chamber that is sloped to minimize medication waste due to dead space, before finally getting atomized in the ultrasonic transducer here and entering the mouthpiece. There, a pressure sensor helps to nebulize medication only when the user inhales to precisely meter the dose that's delivered to the patient. The nebulizer's main button uses a mechanical lever to release medication from the capsule valve and simultaneously triggers the electrical button in green to turn on the device. For simple, single-step activation during the stress of an asthma attack. To reduce the number of parts compared to that main button, the Bluetooth connectivity button is built into the housing and uses the elasticity of the plastic to reliably spring the lever back into place. We used heatset M2 threaded inserts to secure the electronics and keep the buttons and USB charging port correctly in position and prevent damage to sensitive electronic components. We also worked closely with the EEs to design the housing and the stack of printed circuit boards in the most compact way possible. A snap-fit door provides easy access to the fasteners, electronics, and batteries for ease of assembly and testing.
Our first experiment was testing the atomization rate of our ultrasonic transducer by nebulizing 1 millimeter of water, and that's the one we see here with the pipette. We measured a 0.006 to 5 milliliters per second atomization rate, which equates to a rapid 5.76 seconds to dispense a rescue dose of 0.5% of albuterol. We also printed several prototypes and this test part right here in order to test the tolerance, clearances, and attachment methods and material strength. And we found that 0.6 millimeter were needed for clearance fit and 0.2 to 4 were needed for lip and groove attachments. We also conducted a leak test and found leakage through the layer lines of the 3D prints. So we see lip and body with shellac, and we printed the capsule in resin for higher resolution. And finally, we tested the mouthpiece one-way valve here that we have it with the balloon on the far right. And it successfully lets the air out when the user exhaled, and it sealed when the user inhaled. And here is our final prototype with all the electronics fitting in the inside. And for future, instead of using a 3D printer, we would like to optimize our design for injection molding to allow for high volume production and eliminate leakage and create a better surface finish. We also want to add a water chamber for self-cleaning on the go. And finally, we want to explore the capsule valve designs to meter the dispensed doses better and keep the medication more sterile for the future.
Now moving on to the smart pin. Our project scope for the smart pin is we needed to make our device as small and as compact as possible. We also needed to select our components such as the sensors, the microcontrol unit, and the battery so that our pin can perform what was required while still being as small and compact. We also designed our housing around the electronic components that we selected. So the description of our design for the smart pin is that it needed to track and automatically collect particulate matter, volatile organic compound, temperature, and humidity data. It also needed to communicate with the smartphone app via Bluetooth and upload all of the environmental data that was listed in the bullet above when the Bluetooth button is pressed. So it manually and can automatically collect all of that data. The battery status also needed to be indicated on the smartphone application, as well as collate the smart nebulizer and smart pin data into one place. So on the EE side of our inner components, starting on the leftmost image, we have our microcontrol unit, the custom PCB designed by our EE team, the temperature and humidity sensors, and then we have our VOC sensor and the PM sensor with a built-in fan. And then on the rightmost image, we have our battery and our additional fan to provide proper airflow to the sensors on the front side of the pin. On the ME side of our design, this is our housing design that we came up with. We have our battery mounting case, the PCB mounting fixtures, and the ventilation holes which let air come in and out of the pin so that the sensors are reading accurate data. We have the LED hole where the LED is either flashing blue or solid blue depending on if you're connecting the pin to the smartphone app or if you're manually collecting data. And then we have the PM sensor fan hole which brings in air for that fan that's attached to the PM sensor. We have the Bluetooth button hole, the power switch hole which turns the device on and off, the necklace holder because our device is worn as a necklace, and then we have the USB charging hole so that you can charge your device.
So for our experiments, we tested the PM sensor using car exhaust, incense, and cigarette smoke. And we did this to see if the PM sensor would pick up different amounts of particulate matter when placed under different conditions. Similar to the PM sensor for the VOC sensor, we used those same conditions while also adding on hand sanitizer and rubbing alcohol. For our temperature humidity sensor, we compared the indoor and outdoor air to the daily weather report. And to test airflow through the system, we placed 3 temperature sensors in between the electronic components, and we tested with the main fan on and off to see if there would be a temperature difference. In our results, we noticed that while the main fan helped circulate air and cool the system, it significantly affected the sensor data, and you can see that with the lower trend lines on the graph down below. So for our future improvements, we would like to improve the design of the pin by adding baffles inside the housing. We also want to shrink the inner components and also shrink the housing. And we would like to implement the smaller fan that our team has already purchased instead of using the current fan that we have. So throughout this capstone, we found that it is really important to constantly communicate, and that the design, testing, and 3D printing process all take a really long time, so it's really important not to procrastinate these steps. Lastly, collaboration across divisions is extremely important to help the overall flow of the project. Finally, we would like to give a special thanks to our EE team, our project sponsors, and our advisors for helping us on this project. Before we move on to the EE portion of our presentation, do we have any questions so far?
Let's thank our speakers before we take questions. One question now, then the double E team, and then more questions. By the way, E-Man had to go run off and do something, so I just jumped in. Questions? Colin.
I have a question. So then you guys 3D printed a lot of different iterations of the device. I don't know what material that is, but in the final device, what material would you guys use to make sure that it's safe and so on?
So it's actually a little bit of a combination of materials. It's actually a little bit of a combination of materials. Most of the parts are 3D printed out of PLA. Which is, the material itself is mostly food safe, but the gaps in the layer lines can harbor bacteria. So you certainly wouldn't want to 3D print a production model. We also have some parts, including the smart pin, that is resin printed, and that is not a food safe material. but it's much higher resolution, kind of a better analog for what a production model would look like.